Hello and welcome to our presentation on machine reading of unstructured maintenance work order records. My name is Caitlin Woods and I'm from the University of Western Australia. The work reported in this presentation was done as part of Yi-Yang Gao's UWA Masters of Engineering thesis. Since then, we have developed a new research group at UWA known as the NLP-TLP group. This group is performing ongoing research in this area. Engineering data is distributed across a variety of sources, both structured and unstructured. Examples of semi-structured texts include procedures and equipment manuals, whereas unstructured data sources include safety records and operational shift reports. Much valuable information is locked away in these unstructured texts. However, when text is unstructured, information is difficult to extract, as this task requires sophisticated natural language processing techniques. Existing natural language processing, or NLP techniques, are difficult to apply to unstructured text from the engineering and maintenance domains. There are several reasons for this. Firstly, engineering data is inaccessible commercial data that's generally not shared among the community. This means that natural language practitioners have limited data to train their NLP models. In addition, existing NLP work for engineering data has largely focused on one part of the asset lifecycle, the design phase. There has been little work focused on the in-service or maintenance phase, where textual data largely comes from in-field technicians. Because this data comes from technicians, it contains much engineering jargon and abbreviations that traditional NLP approaches tend to struggle with. Finally, there are no widely agreed upon or used approaches for entity typing and semantic representations in this domain. At UWA, we have developed a research group called the NLP-TLP UWA group, focused on NLP solutions in industrial maintenance. This group consists of professors, postdoctoral researchers, PhDs, and honours students with a range of expertise including engineering, computer science, natural language processing, and linguistics. The datasets that we're particularly focused on contain maintenance work order short text data. Ongoing work in the NLP-TLP group falls into three main areas. The first area is in annotating our work order data, ready to be used in NLP applications. The second area involves using these annotations to train NLP models that can tag large amounts of data automatically. Finally, the third area is focused on applying tagged work order data to real industrial use cases. One such use case is maintenance strategy validation. The paper that we're presenting today represents an early phase of NLP-TLP efforts at UWA. The main focus of this research was to explore the domain of maintenance short text, choose appropriate entities to tag, and identify domain-specific characteristics that can be used in future tagging efforts. As I mentioned earlier, the dataset used in this work is maintenance work order data. A work order is created when a technician out in the field identifies a problem with a piece of equipment. The technician will generate a work order record in a computerized maintenance management system, or CMMS. This work order record will contain structured data such as the date when the problem was found and the functional location of the piece of equipment. In addition, the technician will include a short description of the problem and work that needs to be done to fix the problem. Examples of short text are change out leaking engine, AC not working or aircon not working, and engine left valve leaking. This short text field contains valuable data, such as whether we've seen an end-of-life event on the equipment. At the moment, there is no way to extract this data automatically. In this paper, we proposed a pipeline to extract named entities from work order short text. However, we needed to do some thorough pre-processing. This is because the short text was littered with engineering jargon and abbreviations. The first pre-processing step was to separate the short text into individual terms, or tokens. Our analysis showed that the short text typically had between 2 and 8 tokens. The next step, the semantic transformation step, aimed at reducing the overall size of the vocabulary by transforming the tokens, such as equipment IDs, into a standardized token, such as equipment_ID. Next, spelling correction was performed, and the words were lemmatized so that all plurals were removed from the data. Finally, some known abbreviations, such as T_converter, were transformed into their full text form. In this case, it would be talk converter. The only standard pre-processing step that we did not perform was the removal of stop words such as not, and we will discuss the significance of this later. Once the data was pre-processed, we could then move on to start detecting named entities. In this work, we decided to tag 3 different named entities that we considered to be valuable in our work orders. These were symptom state, maintenance activity, and maintenance item. The task of tagging each named entity was separated into 3 different modules. Each module was performed sequentially. The first module was the symptom state module. Examples of symptom state include not lifting or is broken. In developing the symptom state module and examining our dataset to learn how we could do so, we found something very interesting. We found that if we separate our work orders into n-grams, that is, a group of words that occur together, then the head word or the first word of that n-gram is significant in determining the state. For example, if the head word is not and the tail word is lifting, then not lifting is a state that we can find and tag. After tagging our symptom state, we then moved on to tagging maintenance activities. These are terms such as replace or repair. The key learning that came out of this step is that there are in fact a finite number of maintenance activities that were found in our maintenance work order text. We used a dictionary of 103 maintenance activities and were able to use this dictionary to tag work orders with a really high accuracy. The final module is the maintenance item detection module. Items include engine, water pump, or starter motor. In creating this module, we learned that n-grams form a significant part in finding maintenance items as well. We found that if an n-gram appears regularly in the short text and is not a symptom state and is not an activity, then it is likely to be a maintenance item. This, combined with a dictionary used to detect well-known single-word items such as engine, formed our maintenance item module. When developing our item detection module, we found that if we sorted the extracted maintenance items alphabetically, we could then start to reconstruct the asset hierarchy from the maintenance work order text. For example, if we have a compressor, the item tagging module was able to detect lower level items such as compressor mount and compressor mount bolt. This was just another interesting lesson that we learned from this tagging exercise. I also mentioned earlier that we did not remove stop words in our pre-processing stages. Common English stop words include is, and, or not. In our pipeline, stop words were not considered until later on in the maintenance item module. The reason for this is because these words are crucial in our understanding of the maintenance text. For example, in the maintenance work order, engine is not running. It's referring to an item, the engine, that is not running as it is supposed to. However, if the words is and not were removed before our symptom state detection, the work order would read engine running and would hold an entirely different meaning. After running all 3 tagging modules over the work order dataset, we ended up with a list of work orders with symptom state, activity, and item tagged. We validated the automatically tagged dataset against a set of records that had been manually tagged by a subject matter expert. We compared the results of our pipeline to a base pipeline that used well-known NLP technique known as part-of-speech tagging. In the base pipeline, all detected verbs were considered activities, nouns were considered maintenance items, and adjectives were considered symptom states. We calculated the accuracy of each pipeline using the Jaccard Index. This is a measure of similarity between two sets of tagged terms, and found that our pipeline outperformed the base pipeline in all three entity types. I'd also like to mention that code for this pipeline is written in Python and is available upon request. As I mentioned earlier, the pipeline that I've presented today represents an early stage of ongoing work in the NLP-TLP group. Our group meets weekly to annotate maintenance work orders in a collaborative way. In these meetings, we're working towards creating a gold standard of tagged work orders that can be shared among the community for future NLP efforts. In addition to our tagging efforts, we're also working on developing models and visualizations using our tagged maintenance data. This image shows how our tagged data has been converted to a knowledge graph in Neo4j by one of our postdoctoral researchers, Michael Stewart. More on the research that's going on in the NLP-TLP group and an online demo of this maintenance knowledge graph can be found at our website. Thank you very much for listening to this presentation. Feel free to reach out to myself or Professor Melinda Hodkowitz if you have any questions about anything I've presented today.